Okay, thank you.
Yeah, okie dokie. So X-train head, let's see what we have. We have encoded columns and our categorical columns are turned into numbers and our numeric columns stay numeric. So now we can model. Before making any models, I want to see what my baseline accuracy is. So if we go with the conservative prediction of everyone perishes on the Titanic, we're right about 62% of the time. So if your model beats baseline, then there's value in modeling. If your model doesn't beat baseline, then there's not any value in modeling, right? The reason why there would be value in modeling is if the features are good predictors of the target. Does that make sense? Like if the features are not good at predicting the target, then like the baseline that's based off of the mode of the target will perform better, right? That's the way to read that one in English. So let's make our first tree. We'll make the tree, fit the tree, use the tree to make predictions, and then classification report on those predictions. And what do we have? Okay, we have accuracy of 78. Not bad, it's better than 62. So there is value in modeling. And now the name of the game is to see, okay, let's see what models perform like on train. Then we'll see what they perform like on validate. And we're gonna play around with, we're gonna fiddle the knobs and work with the dials on the hyperparameters. The arguments that we were working with here are the minimum number of samples per leaf and then the max depth. You can change any parameter. You can run through and loop through every possibility. It will make your laptop burn a bunch of energy, but you'll do a bunch of modeling. Okay. So if we wanted to manually, which I don't, but it's here in the notebook for your benefit, manually produce confusion matrix, we can manually produce accuracy, true positive rate, false positive rate, true negative rate, false negative rate. And you may notice from some of these that precision, for example, true positives over true positives plus false positives is there, recall is there as well. And I sent a link to the Wikipedia article on the metrics yesterday. Like precision has 5 names and recall has like 4 or 5 names. It's not because people are trying to confuse you. It's because some of these terms came from the life sciences, some came from medicine, some came from statistics, right? Cool.
Hey, Ryan.
Yeah.
You spoke to your code where you make it
Where I make the,
that confusion matrix right there. Yeah. Okay, that's
there's our friend Ravel. Flattens an underlying data set. Yeah.
For the training person, then the prediction. That's what I was looking at. That's, yeah. I was thinking it was train and why prediction. As the documentation says, why you follow by one prediction. I'm confused because we got similar things when you did it. Your output was similar.
True in predictions, true in predictions.
I think the one above, the one above, yeah.
Oh. True and predictions. Yep.
Just lost it. Top of it.
Yep. Because the underlying data didn't change, right?
Yeah.
Cool. Awesome. Then we've got
Sorry.
all the metrics. Yeah, go ahead, Kate.
I had a question on that just because like I talked a little bit with Adam about it yesterday, but
Sure.
I just feel like if we look at that code, especially if we're raveling and assigning it to TN, FP and everything else,
Yeah.
that only works. It works based off the auto sorting of the labels.
Sure.
So if we want to use that code again, it's not going to work the same based on our positive because it's going to resort. And I wanted people to be aware.
Okay. Yeah. The only time I ever actually output manually confusion matrix stuff is when I'm going through these exercises. I use classification report for real work. If that helps. Because I don't want to do arithmetic. Right, I want Python to do arithmetic. Cool, cool, cool. Are we cool to move forward? I agree with you. Let's get loopy. So why would we get loopy? Well, in this loop right here, I'm going from 2 to 10, inclusive of 10. And what I'm doing every time through the loop is changing the max depth. So I'm going to make a whole bunch of different random forest models, fit those models, then make predictions with them and produce a classification report and show what we got. Okay, so there's a lot of numbers on the screen. To simplify things, right, we can focus on accuracy, and we see accuracy starts at 82, 84, 85, 86, 89, 92. This should go up, as we might expect. Right? But what we need to do is not look at a model's accuracy on train in isolation. We need to check and see how things do in sample versus out of sample. So when I say in sample, what does in sample mean to y'all versus out of sample? Yeah, in sample is part of the train, and out of sample is data that the model has never seen before, which would be validate, and which would be train, and which would be data in the wild. So now we're going to make a random forest classifier. We're tuning the depth. We're only playing with one hyperparameter here. Make the model, fit the model, use the model to make predictions. In this case, the score property here, we're only focused on accuracy for this one, just for argument's sake. And then the output will make, oh, look at that. There's an empty list, and we're filling an empty list full of dictionaries. You better believe there's a data frame around the corner. So we'll specify what the depth is for that particular tree, the train accuracy for in sample, and the validate accuracy for out of sample. And let's see what we have here. It's going to take a minute to run because each one of these random forests, if it's defaulting to the number of trees is 100. So each time this loop runs, we make 100 trees in a forest. They hold a little election to see what they all agree on and where the consensus is, and then they make the predictions.
For the score, you pass
Yes, we have to for the score. It's going to take in the X and it's going to take in the Y. And what it's doing is making predictions based on train and comparing those predictions from train to the actual. So what's going on underneath the hood of score is it's calling the dot proba, the probabilities function. We don't have to manually call that probabilities function. Okay, so we've got increasing accuracy starting at 82, going all the way up to 99, right? But we also see a couple of other things happen. Train accuracy goes up, validate accuracy goes up, then it goes down, then it goes back up, and it goes back down. So the difference, if the train accuracy is higher than validate, then folks, we have an overfit model. And how do we decide which model is the right one to use? We want a load difference, but we see that the difference kind of peaks out and it gets higher and higher. So we get more and more overfit the more depth that we have here. And you know what? I would rather take, I know this might sound a little crazy, but I would rather take an 82% in sample accuracy with a 77% validate accuracy. I'd rather take that one because there's a low difference and the out of sample accuracy is pretty acceptable. I'd rather take that than something that's like 99, 80. Does that make sense? I'd rather take like 82, 8277.
Probably want to, like, a couple below it, would that be the best, because you have, like, the third one maybe, or.
Third one?
Yeah, or.
Yeah,
so you
yeah.
have, like, the highest accuracy without changing the difference.
Oh, the highest accuracy invalidate? Yeah. I'd rather have something with a small delta and they're both reasonable rather than super high train and basically the same validate. Because validate is out of sample data.
I was saying, what about two, but is there even a difference between the first one, like 0.000? The difference in the limit
Where?
between
These two?
those,
Yeah, there's a little bit.
I mean, how much take the next step?
Those are all valid. There's not a right answer. Welcome to data science. There's never a right answer. There's always just like making a judgment call, right? Oh yeah, Arsene, go ahead.
So I have two questions. The first one, you or Adam may have already talked about it, but I don't remember, or maybe I wasn't paying attention at that time. But why is it that we need to run, like suppose we're running all our simulations on the same notebook. We selected our data, we acquired it, we prepped it. And when we get to comparing train and validate, we need to run validate and train at the same time. Like I tried to just run validate, like just running the cell of train above, but it didn't work. Like it gave me an error. It told me that I need to fit the data first before I can validate it. So I assumed that it wanted me to do that in the same cell. That happened yesterday with what is it called? The previous one. What's the previous one we did?
The decision tree?
A decision tree. My brain is tired. Sorry.
Okay.
So that's the first question. And then the second question is, why not 84? Why not max depth 3? Because that is a little bit higher, but it may give enough depth, of questions to,
Sure. Yeah. Let's talk about that first question first. I'd have to see your code and see the error message to be able to answer your question effectively. But I will share, the code does not care if you talk to the validate data set or not. The code doesn't care at all, right? If I were to comment out this validate accuracy and just run this output, or if I were to only run on train or only run on validate, the code doesn't care. Human beings care. So but it's important to know, looking at the metrics of a model on train is only valuable in that isolation to see if you beat baseline. When we look at a model and its performance on train, even if there's 100%, I can't tell you if it's a good model or not until the model sees unseen data, out of sample data, the validate set or the test set, or data in the wild. Yeah. So the reason why we are evaluating models on both train and validate is because that's how you validate a model. That's how you evaluate a model. You turn it upside down and you see how well it does on the test, on the practice quiz, and see how well it does on the real quiz. Here, the practice quiz is trained and the model trained on the practice quiz, and the real quiz is validate. And then the final is the test data set, right? Did that speak to your first question, Arsene, with a sufficient depth? And then your second question is, why don't we focus on row number 3 or row number 4? Yeah, you made a compelling case for it, right? Made a very compelling case for it. That validate accuracy, 799. Maybe you've got a mental reason why you want the accuracy above 80% on both, even if the difference is a little higher. a lot of this stuff is rounding errors, right? So I'm not gonna get too bent out of shape about rounding errors, but get bent out of shape when you have like a 20 percentage point overfitting. Avoid that, please. Great.
Quick question, is it a sign that we did something wrong if we got different numbers? I see similar trends.
Yeah. No, there's randomness in the model, right? So there, like random forest has a lot of randomness in the model. We are even setting the random state, but if we had a different random state as part of our train test split has other randomness too. So I'm not gonna like four decimal places in is about 3 decimal places in is about when my give a crap starts going away, because there's so much randomness in a random forest. There's randomness in the split, there's randomness in the model. So if yours is like orders of magnitude different, then let's worry about it. But if we're rounding errors.
I did the inverse because the question said to increase your mid samples, decrease your max depth. So I
Sure.
started from the other side, but it just flipped them. So it's.
Oh, yeah. I think I'll make it to that one next, the increase one and decrease the other. So if you've got a happy little data frame that's all a bunch of numbers, guess what you can do with a happy little data frame with a bunch of numbers? Folks, you can plot it. And check out what we have visually. We have train accuracy increasing, hitting a plateau. Validate accuracy increasing, wavering a little bit, plateauing, and then the difference plateauing as well. So you could pick a visual point that you like the most as well. And we could play with other hyperparameters, right? The default number of trees per forest is 100, but you could crank that up to 1,000, right? If you felt like it.
Which I did. It took a long time.
Which Andrew did, and it took a long time, yeah. Yeah, because it's not caching any of the output, right? Yeah, so let's get more loopy and we'll do some more visuals. What I'm gonna do with this second loop example, we're going to increase one value, decrease another value as a hyperparameter. So max depth is how deep your tree is. The minimum number of samples per leaf, that's the minimum number of classified data points per endpoint in the tree, per leaf. That's what a leaf is an endpoint of your tree where it makes a final prediction. Lincoln,
I was thinking about the sample for the G. Specify with one sample, or you just have to stick with what the
I don't think you can specify what samples. Look, we can check the docs. I'm not gonna pretend to know everything, so I will look at the samples. Now, this doesn't tell us, I don't see anything in here where we can specify samples of a certain kind. I see minimum samples of leaf, minimum samples per split is another hyperparameter, but we're not saying which samples. Yeah, and that's always going to be a function of the data itself and how
how you create a trade.
not so much how you create the train, but just like how the data exists in relation to itself, all the different data points. Because if our proportions our proportions will be different, right? We have a different rate of churn than we have rate of titanic deaths. And then all the different features are different too, right? The embarked town doesn't relate to internet type. They're both categorical, but they're so different, right? So in a lot of ways, these hyperparameters have some importance to the model, but really the model's performance is going to be based on the data itself, first and foremost. Yeah. So we're increasing min samples, we're decreasing max depth. How do we do that? So I'm making an empty list called metrics, and we're going to build up a bunch of dictionaries to put into that list, append into the list, make a data frame. If you haven't picked up on the pattern by now, it's a heck of a way to make data frames, right? And I'm specifying a specific number. I'm going to start my max depth at 20 and check out what I'm going to do with the for loop here. I'm saying for I in range 2 to 20, I'm starting at 2 because 2 is a good start, right? The depth variable will be max depth minus I. So the first time through the loop, our depth will be max depth minus 2, actually. The number of samples will be 2. So depth goes down, n samples goes up. And then where do we use these variables? Well, we use them every time we make a new model. We set the max depth to the depth variable, which is going down each time. We set the minimum samples per leaf. And that minimum samples per leaf, that's another way of controlling what each tree looks like, right? So that's going up the random status set. We fit on train, we evaluate train, we evaluate on validate, and then we produce an output for each variable, for each different model. We'll have min samples per leaf as the n samples value. The max depth is the depth variable that's changing every time through the loop. My train accuracy is my n sample accuracy variable. Like conceivably, you just put forest.score on the right-hand side of that assignment, right? Validate accuracy is the forest score on validate data. We'll append our dictionary to the list, and data frames are lists of dictionaries. The data frame constructor loves lists of dictionaries. And we have some numbers. Looks like our training accuracy is going down. Our validate accuracy is also going down and then up and then down. We plot these out if we feel like it. This is a pretty reasonable chart, right? And we want to go for the least overfit. Again, overfitting is going to happen sometimes. We can make a nice little scatter plot between the depth and the difference. So we see as the depth of the tree increases, our overfitting increases. The difference between train accuracy minus validate accuracy. So the deeper your trees go, the more they're memorizing the practice test, and they're not as flexible on the regular test. If we were to plot minimum samples per leaf, now this is interesting. The higher our minimum samples per leaf is, the less overfit we are. Pretty cool. And we can plot out the difference and the accuracy. So we have a pretty high, this high data point, we have a high difference between train and validate accuracy, but that validate accuracy is 82. That's pretty good. There's not a single right answer in here. There's judgment calls. The judgment call that we'll make here is, well, I don't want to be super overfit, but it's much more likely that the rest of our data set will look more similar to validate than it will train, just because we haven't seen the rest of the world yet. We want to increase both minimum samples per leaf and max depth. We simplify, we don't have the depth is equal to max depth minus I, we just increase both. And this will give us some new numbers. And let's see what we get when we plot them. Okay, they're both kind of flat. I find that's really interesting. When we increase both the depth and the minimum samples per leaf, we go up a little bit, we go down a little bit, we kind of waver around right now. Which begs the question, what if we fix the depth and isolate only tuning minimum samples per leaf? Let's see what we get there. I'll run the data frame that puts all of that together. And we will, interesting. So if minimum samples per leaf increases in isolation, both metrics get worse over time. So feel free to use this notebook as a tool for evaluating and plotting out your differences. You could even use the chart here the visualization, change your variable names, and the for loop with the data frame, you could use this with other models, other hyperparameters, etc. If you have hyperparameters that are like a categorical set, you could loop through the categorical set of hyperparameters. The sky's the limit, right? The sky's the limit. And sometimes a certain set of change one hyperparameter, change another hyperparameter, it's just right. A lot of folks will think that hyperparameter tuning is the yellow brick road. Usually the yellow brick road is more training data, better quality data. That's usually, that's the best yellow brick road. Yeah, question from Ryan Miller. Go ahead.
Yeah, thanks, Ryan. So just in sum, as part of the good data analysis process is you're going to do the tuning of hyperparameter. You should do it every time, hold ones in isolation and,
Right.
Okay.
Right.
Depending on how much time you have.
Depending on your time. Yeah, absolutely. Absolutely. Subject to time constraints and resource constraints. Right. If you were trying to loop through stuff and you've got a mental block and that's going to cost you a day, just make a different model, right? And see what else you can get. Try a different model entirely. It is possible to try make a hypothesis space of every possible hyperparameter. That's a good way to always have your computer calculating things. There's benefit to it, but usually simple models do better. And the number one way on planet Earth I've seen to make better models is better data that's a better predictor of the target. Sometimes your finding might be our features are crap and baseline is pretty good. So we probably need to measure something we're not currently measuring. Cool. This is all on GitHub, and I have a question from Andrew. Go ahead.
So maybe a little bit, you saying earlier we were looking for a low gradient.
A low difference, yeah.
I'm more with that.
Sure.
Can we define low because that's kind of a relative term.
It's all relative, yeah.
So I'll give you an example from my data. I
Sure.
found my best reporting validation accuracy was 86%. The
Okay.
difference was about 4.5%.
Okay.
Right, but then just below that, I found the validation accuracy of 85.5 with a 1.4% difference. So which one would you prefer? That's 86, 4.5 difference, 85.5, 1.4 difference. Those are really close, I know.
You could make an argument for both. In that case, because based on the numbers that you quoted there, I would go for the smallest difference. But like smallest difference in isolation might not be the best. Like in this chart out here, I have the smallest difference, 18 max depth and 18 minimum samples. I think this is a random artifact. 0.3 is better than everything else, but really like the difference is pretty flat across this whole board. So
Okay.
I'd pick one of these 0.5s or 0.4s. Say again?
I'm just saying, like, I'm looking for an answer or definition when it's really like relative to the data.
It is always going to be relative to the data you're looking at. That being said, if I have a really high train
Right.
and accuracy and a really low validate, like 99 train, 70 accuracy validate, that's a pretty high difference.
Yeah.
And I'd rather have a model that the train and the validate are close rather than the train being better.
I think my question was,
Yeah,
where do we define close? Is 1.4% or 5%? Are those both close?
they're both close to me. Yeah. 1% closer. Yeah.
And
Lincoln?
also just an additional question. for
Sure.
us all about is like, where do you kind of want to throw away the model if you like where the delta is like a lot, like or like a little bit. You know what I mean? Like when do you go like, okay, this model just sucks because like the
Yeah.
difference is just so much and you just
Oh, yeah. If you have an overfit model, usually things you can do are get more data if you're in a position to get more data, or try a different model, try different hyperparameters, try a different model entirely.
from the main stack.
Yes, the time to throw a model away and ignore it completely is when it can't beat baseline. It's not even worth your time. If it beats baseline, it's probably worth your time. Yeah. And when it comes to modeling, some of the code that takes the longest time with modeling is building out models and loops and comparing the results. It's really not even the modeling, it's just the Python coding. Yeah. Yeah. Cool. Cool. Any closing comments, remarks, questions on random forests before we shift gears?
Just thinking about when you're doing visualizing results, and you didn't really like that.
Yeah.
So the columns in there, how do you know when to throw columns in there and see that visualized properly? Because that's my thing, like.
Well, yeah, there's a lot of, you need to specify what columns you want to show.
They're all like.
Yeah. Yep. Feel free to use it.